Good morning and thanks for coming. My name is Mike Goldstein and I serve as the director of the Alaska Coastal Rainforest Center. And I'm very excited and thankful that you've taken time out of your busy schedules to be here today. The Rainforest Center, as some of you might have heard last night, and for those who weren't here, the Rainforest Center started with an MOU between 6 founding partners in 2009 and has grown to a partnership network of 16 organizations. We have them listed on the banner over here, and they're as well in your program. So I'd like you to take a look at that at some point and see the breadth of the nature of the organization. Today's organizational framework is designed to bring us from then till now and from broad, holistic across the globe to the Pacific Northwest, Southeast Alaska, British Columbia. And so this international plenary does that. And what I've tried to do in the course of the 3 days is have someone from each of our partners come and provide some opening remarks and welcome. And today we're honored to have President Edward Thomas from Central Council of Tlingit and Haida. So I would like to introduce Leilani Knight McQueen, who's the environmental coordinator, and she will introduce President Thomas. Leilani and I started working together 6, 8, 10 months ago as we tried to find some pathway forward to bring our organizations into a framework. Now, the University of Alaska Southeast, where ACRC is based, has existing relationships, as does the Forest Service and many of the other partners. But we wanted to formalize that as part of the partnership network. And Leilani and Ray Paddock and a few others have made significant strides to help us do that. So I'll welcome Leilani. Thank you.
Good morning, everyone. We're delighted to be partners with the Alaska Coastal Rainforest Center. The vision and mission and allowing Central Council as the Indigenous peoples representation in a regional capacity was available and welcomed to be a part of the strategic planning for the Alaska Coastal Rainforest Center. And in that, we were able to support traditional ecological knowledge in science and are willing to support those efforts to gain that knowledge and a venue for being able to contribute in that way. And so in addition to that, by having the likes of President Thomas to support the work that we do in the native lands and resources is a tremendous benefit to the Alaska Coastal Rainforest. I'd also like to recognize my staff, Kate Jensen, our youth specialist, if you'd stand, Kate. Ray Paddock. And I have another staff member, Helene Bennett, who's making sure our president gets reelected. She's working on the floor for Tribal Assembly. So, and then my fearless leader and guider clearing the way for me is Desiree Duncan, program manager. And sheesh. Again, getting back to what Central Council offers as a partner to the Alaska Coastal Rainforest via our president and his reputation as a national tribal leader. He's continually moving us forward, not just Tlingit and Haida people of 27,000 citizens, but he works tirelessly over the work for national tribes. And he's well respected within the national level, at the national level, by tribal leaders as well as presidents of the United States. So President Thomas currently serves as the president of Central Council of the Tlingit and Haida Indian Tribes of Alaska. He was first elected as president in 1984 and served in this position until retiring in 2007. And thank goodness he came back in 2010. As president, Mr. Thomas is responsible for the overall administration of all operations of the tribe, representing more than 27,000 Tlingit and Haida Indians worldwide, oversight of over 200 employees, manages a huge budget. implementation of general administrative policies of the tribe, and completion of all actions of the Tribal Assembly and the Executive Council. And in that, I want to add that it is through his guidance and leadership and insistence upon us creating programs within Central Council, creating programs that are beneficial, first and foremost, to the tribal citizens and moves the efforts forward. And then he allows us to create those kinds of programs. So very clear direction about where we belong in terms of collaborations and the work that we do. Thus, we're here at the Alaska Coastal Rainforest Center as a prominent partner. President Thomas also serves as a board member on Sea Alaska Directors, and he also is a special trustee for the Indian Affairs Department of Interior. President Thomas is also elected to the NCAI, which is the National Council for American Indians, and holds the seat as secretary there. And I'm going to go ahead and leave it there because he's got a lot of good things to say. So, President Thomas.
Thank you very much for the introduction, Leilani. Honorable people, it's good to see you here today. Tlingit ayachat, zach yuchat tuusak, shanskadek yuchat tuusak, skilkwidans in Haida. I'm a Tlingit, and my Tlingit name is Zahu, the name I was given at birth, and I also have another Tlingit name, which is dog salmon name of Shanskadek, and I was honored with the Haida name of Skilkwidans. I'm a dog salmon of the Raven Moiety, and my father's people are the wolf people. I'm truly honored to welcome you to Southeast Alaska, the ancestral homeland of the Tlingit and Haida people. Southeast Alaska has been our home from the beginning of time. Now, there are people that say we must have migrated from the other side of the world across the land bridge, but that was the other people, Tlingits. We were from here. And legend has it that during the Ice Age, we were forced off our homeland, and I heard that you heard a story about us returning. And there are some findings in our region that verify that our people were here at least 10,000 years ago. But if you look at the era of the Ice Age, you'll see that Southeast Alaska was covered by the Ice Age approximately 10,000 years ago. The other bit of information that I offer about us not migrating is that when people move, they take their language with them. And you'll have a hard time finding any of the dialects of the Tlingit across in Asia and northern Siberia. And so it really does not make a lot of sense to keep reinforcing the old myth that somehow we had to come from that side of the world because that's where history was written first. And I don't bring that forth as a point of debate so much as a point of who we are as a people. As pointed out, we have approximately 27,000 tribal citizens nationwide, and approximately 17,000 live in Southeast Alaska still. But we have always had a strong relationship to the land, as many people around the world do with their homeland. When I look at the issue of global warming, it's one of those things where in early times we are thankful for global warming because all of the glaciers retracted and left our homeland back to where it was years ago. And so for that, we are thankful. But in current modern times, you look at the amount of global warming, it gets you concerned. I was looking at some of the materials out there, and we had some of our own when we had the workshop here on global warming. And you can see that the glaciers in just my generation have really retracted substantially around this part of the country. And that brings concern because in our forest, we rely a lot on moisture. Now, I'm not sure why you call this a rainforest. It's nice and sunny out there today. But in all truism, we do have a lot of moisture and a lot of rain, and we rely upon the snowfalls to replenish our streams in the summer. During my younger years, I was a commercial fisherman, and so really learned to appreciate the value of our streams, because when the streams were in some ways desecrated or the fish were harvested, they really did not replenish very rapidly. It took many, many cycles to replenish the fish to the streams once they were either damaged or the fish were desecrated. And so the environment to our people is very important. And in modern times, you know, when you talk about Native Americans, particularly Alaska Natives in this region, when you think about our relationship to the land, it's always in terms of, well, they're concerned because of subsistence. While that is true, there is a broader connection of our people to the land than just relying upon the resources for our subsistence uses. Our people are engaged in some of the commercial, we're engaging in some of the tourism issues or opportunities, and we are part of the society that occupies Southeast Alaska. And that creates a lot of concerns to us that we are seeing the changing to our environment that are in many ways not very healthy for us. One of the things that I'd been concerned about in early years was the issue of water blooms in our area. We have ships that come across the ocean, and they pump ballast water into their ship so that it would not roll so much. And then when they come to our shores, they pump it out, and that water has things that are foreign to our homeland, and so it creates a bloom and creates a problem in disrupting the makeup of the ecosystem of our shorelines. And so those kinds of things are very bothersome. Southeast Alaska as a rainforest is a little unique. If you've been out and around, and I heard you went out on a boat yesterday, you see that there are many waterways in between and breaking up our forest. Those were the highways, the early Tlingit people. But probably the most important part of that, there are many creatures in that environment, in that ecosystem, that have to have balance. And one of the major concerns I have as a person that's lived here all my life is the issue of overharvest of herring, for example. Now that might sound very isolated and something that's only going to affect herring. But herring is such an important part of the food chain of not just fish, you know, like salmon, but also a lot of marine mammals that depend upon the herring. And so when we talk about the forest of Southeast Alaska, or the Tongass National Forest, we must keep in mind the coastal zone as well. And we must keep in balance those resources those living beings within our homeland here, so that so that you don't exploit it to a point whereby it's out of balance. And when I talk about herring, I don't talk about it simply observing one part of our region. Where I'm from, where I was born and raised in Craig, we had a substantial amount of herring when I was a young man, or youngster. And that has, it's kind of spotty nowadays, but south of Craig is Heidelberg, and down there a place called McFarland Islands. They used to have some of the heaviest herring spawn in our region, and it's all gone. And these practices are not something that didn't happen elsewhere. San Francisco Bay used to be a place where they harvested herring commercially. Puget Sound had substantial herring runs. And over-harvesting made those areas now very difficult to find herring. And the rest of the wildlife that goes along with the food chain also suffer as a result. I bring that forth today because as you talk about the broader issues of forests, I hope that we don't overlook the coastal zone and the need to manage it in concert with our forests. When I talk about the homeland of the Tlingit people, and to a degree the Haida, I'm a Tlingit, so I can't really speak about the Haida portion as the relationship, because when we talk about our relationship to the land, it is not simply a physical relationship. It's not simply a commercial relationship. We have a spiritual relationship that has been developed because of our strong reverence to the land and its resources. And you might say, well, how does that work? Well, when I introduced myself, I talked about me being a dog salmon of the raven moiety. And that is my forefathers revered the dog salmon and watched it and analyzed it. And I noticed on one of the booklets out there, there's a dog salmon on, so I thank you for that. And if you look at all of our clans and our moieties, we have ties to the creatures of our region. And when we look at what is happening to our land, we are thankful in many ways that development is making the quality of life better for a lot of our people. We are also thankful that, as I mentioned earlier, that our homelands are not covered with ice. But as we look into the future, I hope that we can develop policies that are going to be more in the area of preserving the way it is, so to speak. And if we're going to exploit them in a responsible manner. That's about all we can really ask for. I really don't want to take a lot of time. I want to make sure that I let you know that we welcome you to our homeland. We welcome you to Juneau. And in our traditional way, normally we would have the Ak clan leader up here welcoming you, and from the Eagle side, the Wishkitan, the Shark people. But I am here on behalf of Tlingit and Haida, and I apologize to those clans for taking the liberty of welcoming you. And but I still feel it's very important for our tribe to make it clear that we really not just welcome you, but we commend you on the good work you are doing on behalf of our world. Thank you very much. Gonna chish hawa.
Folks, there are some more seats up here if you are interested in not standing. So we welcome you to come up towards the front. This is Brittany Lenhart here, and she's touched many of you out throughout this process. And I know I and many of you have already given her thanks, but Brittany is here. Brad Ewing is here. He's been doing most of the setup here at Centennial Hall. I like to say he fell on his sword yesterday because he skipped the boat trip to be here to make sure that everything works right. Heather Bennett's up at the front desk. She's been an incredible support staff for the Rainforest Center. Adam Taylor is here. He's going to help us keep track of time. He's one of our research assistants. Brittany Seavey and Adam Krameritz will be floating in and out over the course of the next 2 days when they're not in class. So the Rainforest Center is 7 people deep right now, and it's through the generosity of many of you and many of your organizations. The Rainforest Center Symposium has a set of sponsors, and I am going to read them off and hopefully not skip any like I did last night by mistake. The University of Alaska Southeast, first and foremost, the home for the Rainforest Center. The U.S. Forest Service, the Alaska region, the Tongass, the Pacific Northwest Research Station, and the Chugach have dug deep into their budgets to help not only with the symposium, but with the Rainforest Center's growth in its early stages. The North Pacific Landscape Conservation Cooperative has also done a fantastic job of supporting us with the cross-boundary data integration workshop and through the symposium, and connecting us with the University of Washington on some database development that we've done. The Wilberforce Foundation has been in it since the get-go, during dialogue with the Tongass Futures Roundtable, Dave Secord before he moved on, and many others. The U.S. Fish and Wildlife Service Alaska region, and particularly Bill Hansen in the local office and the Juneau Field Office. The USGS in the Alaska area has been front and center to help the Rainforest Center grow. The Juneau Economic Development Council, as many as you saw, has just played a really strong support role for the Rainforest Center, particularly in registrants and whatnot. The Nature Conservancy, bringing people from near and far, and bringing in Peter Kariva for last night's talk and for the banquet talk. And I think last night stirred some thoughts, and I hope that today and tomorrow the stirring of those thoughts continues. And of course, Central Council, and thank you to President Thomas and Leilani for being here this morning and welcoming us all. Now, sometimes you ask people to come and give a talk, and they have no idea who you are. Sometimes they know who you are, and you can get them on the hook pretty easily. But in this case, I went and made a pitch to Kirk Johnson, and he had no reason to come to Juneau for this process because he didn't really know who we were and what we were about. And I was so honored and humbled when Kirk gave me actually a fairly rapid yes over the course of a few days. And so I'm very happy to be able to introduce Kirk today. Kirk Johnson is the Chief Curator and Vice President for Research and Collections at the Denver Museum of Nature and Science. Having earned a PhD in geology and paleobotany at Yale in 1989, he started at the museum in 1991. His research focuses on fossil plants, the extinction of dinosaurs, and methods for dating rocks and fossils. His research has taken him to all continents, and he is presently working on projects in Patagonia, Utah, and Colorado. Dr. Johnson is the leader of the Snow Mastodon Project, an effort to understand the amazing Ice Age discovery that was made by construction workers at Snowmass Village in October 2010. And he's the co-author of Cruising the Fossil Freeway, which many of you who have run around Southeast Alaska might have seen. So please help me warmly welcome Kirk Johnson.
It's an honor to be here in Southeast Alaska. I love Southeast Alaska. And I have 45 minutes to give you 60 million years of perspective, so please sit back and hang on. You see behind me a coal seam in a coal mine, and you may see the coal seam, but I'm a paleobotanist. I dig the fossils. I see the landscape that was that seam some time ago. So you see the coal mine, I see the swamp. And that's my perspective. I travel the world looking at the vegetational history of the planet, and of course you live in this amazing temperate coastal rainforest, and that's the topic of the conversation. And I want to give you some context of how this amazing ecosystem came to be. My friend Rachel calls this time travel with a shovel. We use tools, simple tools like hammers and shovels, to go back in time and reconstruct ancient worlds. What's become kind of interesting recently with paleontology is the realization that as we, as humans, change the composition of our atmosphere and thus our climate, we are going to a different climate mode. And fortunately, the Earth's history gives us a nice selection of climate modes to go peruse. So by taking you back in time, I can take you forward in science and give you some idea of what we might expect in the future. I recently sat on this National Research Council panel called Understanding Earth's Deep Past, Lessons for Our Climate Future, which asked the question, how relevant is something that happened millions of years ago to something that might happen in 100 years? And one of the graphs that came out of this thing was this graph, which startled all of us. It shows on the bottom time in millions of years, from 0 to 50 million years ago. It shows on the vertical axis carbon dioxide in the Earth's atmosphere. And you'll note that you can see in the last 25 or 30 million years, CO2 has been below 500 ppm as it is today. But during the warm times of the Eocene and Oligocene, it was maybe as high as 2,000. The red bar that goes across is the IPCC business as normal estimate of what we'll see in the year 2100. So in 88 years from now, if you cross those bars, we have the potential to go visit the Eocene period. It's kind of startling. In 88 years, we can go back 34 million years. That's 330,000 years per year. Think about that. All right, so forests. I love forests. I've worked in lots of forests, both living and fossil. And there aren't that many forests on the planet. And forests move around as climate changes. When the first forests evolved 400 million years ago, and forests have always been in motion. The component genera of trees have been evolving and going extinct. The ecosystems have been assembling and falling apart. The biomes have been coming together and falling apart. Biomes originate, biomes go extinct. And here's just today's forests. These are just today's forests. So sit with me now for the next 40 minutes, and I'll take you back to how these forests got here. I grew up in the Pacific Northwest. This is my home old-growth forest. Unfortunately, not much of it left. Amazing coastal rainforest of Washington State. And just a quick terminological thing for you. This conference is about all temperate coastal rainforests, and so some of you may be more familiar with the Tongass than you are with Valdivia or Tasmania. But just a quick reference. In general, the Pinaceae and the Cupressaceae are more prevalent in the northern temperate rainforests, where the Araucariaceae and the Podocarpaceae are more common in the southern temperate rainforests. That, like many things in prehistory, is just today. And I'll show you this graph because here's a map, hard to see a little bit, but it's a map that shows you that in the late Cretaceous, 60 million years ago, both podocarps and araucarians were here in North America. So the presence of them in the southern hemisphere now and not in the northern hemisphere is really an artifact of extinction, not any fundamental difference. I'll come back to that. I want to introduce you also to three important tree genera just to make the point that time is long, but certain genera have been around for a tremendously long period of time. This is ginkgo. First shows up in the fossil record 170 million years ago. And there it is on my dinner plate in Kumamoto. And the leaf is a fossil from 15 million years ago from eastern Washington. A second genus, Metasequoia, grows today only in China, Hubei province. A very important genus of northern temperate rainforest trees. Not today, but in the past. Fossil again, 50-million-year-old fossil from Washington State. Here's a genus that's 70 million years old. Cercidophyllum, the Japanese scholar tree. Again, a tree that's been around for about 70 million years as a genus. Again, a tree that lives only in Asia today. Again, a tree that's very important as a fossil in North America in the evolution of temperate rainforests. So those guys are there. My friend Ray Troll is fabulous. Every paleontologist needs an artist because we need to be able to communicate with people, and art's the way to do it. This is Ray's time scale. The data are in the strata. I'm going to take you on a trip from the Cretaceous through the present. A few words about time, just so you think about this. We learned yesterday that isostatic rebound around here is up to 3 centimeters a year, which means that Gustavus has come up 6 meters since the ice went away. That's pretty good. You can make a mountain in 1 million years that way. That's uplift. The plates in coastal Alaska move, or have moved, at rates up to 5.9 centimeters a year, which means that over 30 million years, a continent can move 1,000 miles. That's pretty cool. And erosion in the mountains, even if it's a millimeter a year, you can plane off 3,000 feet in 1 million years. Which is you can make mountains, you can get rid of mountains, you can move continents in far less time than individual genera of trees have existed. So the botany watches. So our world today, it's as you learned it. It's got polar ice caps. It's got tropical rainforests in the middle. It's got our present selection of biomes. That's today. Man, our planet has a fascinating climate history. There's sort of been 2 climate states. There have been times when there were no polar ice caps at all. We call that greenhouse Earth. And there have been times when there have been polar ice caps. We call that icehouse Earth. We're presently in icehouse Earth. If you look at this graph, which shows, again, time on the bottom, 600 million years ago to the present, those blue bars are the times when icehouse Earth have been in force. That is to say that about 85% of Earth history, we have had no polar ice caps. This is a greenhouse world with no polar ice caps. What's on the poles when you have any ice caps? You have forests. There are forested poles in greenhouse Earth. So during icehouse Earth, we have these 2 conditions, the glacials and the interglacials. We're presently enjoying an interglacial. It's the one called the Holocene that saw the evolution of human civilization. But it was preceded by cool glaciers, and in fact, a whole suite of them. Here's what the world looks like today, 20,000 years ago, the ice sheets. Bring it in a little bit closer. Put 20,000 years ago, put the ice sheet on top of North America. These are the glaciers we've been talking about. We see fabulous evidence of these out the door here. Now, these things went back and forth like 25 times in the last 2.5 million years. I mean, North America has been scrubbed and abraded and scrubbed and abraded. My southern hemisphere friends call North America a post-glacial wasteland. It's a Brilloed continent. I mean, it's a phenomenal thing. I'm from Seattle. There is what Seattle looked like 20,000 years ago with a Space Needle underneath 3,000 feet of ice. So it's a very different world, and you don't want to have property where the ice comes. We know a lot about this from drilling the ice cores. Here's the amazing 800,000-year record from Antarctica, 800,000 on the left and 0 now on the right. Those ups and downs of the climate on the bottom in black are matched amazingly by the ups and downs of the greenhouse gases, methane and carbon dioxide, as preserved as fossilized air bubbles in those cores. And of course, you're aware, as I am, that our present CO2 in the atmosphere is 393 as of 2 months ago, measured on Mauna Loa, which means that we are far above what's ever happened in the Ice Age. We've said goodbye to the Ice Ages, and we're actually headed towards a greenhouse world. Now, as I say, I'm mainly a greenhouse person, but I'm a broad paleontologist who sees an opportunity. And just 18 months ago, we made an incredible discovery at Snowmass Village in Colorado, which allowed us to experience some Ice Age paleontology. These construction workers holding 3 mastodon tusks, ivory tusks. We responded in force. Remember, time travel with a shovel. And we collected over 5,000 Ice Age bones in 51 days. We moved 8,000 tons by hand with shovels. We retrieved incredible Ice Age animals. This fauna of mammoths, mastodons, giant bison, giant ground sloths shows you how the planet changes over time. These animals are about 120,000 years old. What's also cool is at this site, we uncovered ancient fossil forests. Well, not particularly ancient, 120,000 years, which for me is chump change, I gotta say. We acquired chainsaws and logs that are 120,000 years old and brought them back to the museum. So let me take you out of the ice house and into the greenhouse, which is really our future, and it's a fascinating time. The greenhouse, like the ice house, has 2 different states. In the greenhouse, we have warm periods where we have temperate forests in the polar regions, and we have very brief hot periods called hyperthermers, where we actually get subtropical forests up to the Arctic Circle. Almost unimaginable if you think about it, but I'm going to show you the evidence for it now. So let's move the continents back. Remember, you can move the continents around pretty easily. They're very mobile. At a few centimeters a year, you can move a continent a long way in 30 million years. Take you back to 50 million years, which is a peak global greenhouse. It's the warmest time in the last 100 million years. And I'm going to take you up to a place that is today the high Arctic islands of Canada, several thousand miles above the modern tree line, far north of the North Slope of Alaska up to Ellesmere Island. I had the amazing pleasure of spending 2 summers on Nunavut in the early 80s doing paleontology, and it is an amazing place. Ellesmere Island is the size of Great Britain with about 200 people on it. Axel Heiberg's the size of Ireland with nobody on it. It is like going back to the Ice Age. Here's one of the central Ellesmere ice caps. It's a very odd picture, but note that little thing in the middle. That's a 300-foot high waterfall pouring off, and I'm standing at the base of it there. We explored this vast continent-sized island for 2 summers, and amazingly, here are coal seams. And if you look at those crumbly white things in the coal seams, they're in-place logs. We're 2,000 miles north of the Arctic Circle, 2,000 miles north of the tree line, and in-place tree trunks and standing petrified forests. And you can identify these things by finding the fossil leaves, and in fact, they're metasequoia, the Don redwood, that tree I showed you that lives in China today. Also Cercidophyllum, the scholar tree. Elms. And paleontologists are really good at looking at fragments and recognizing the whole. Here is the central part of a large leaf, a lotus. We worked with Mary Dawson from the Carnegie, an amazing woman who discovered the first pre-Ice Age vertebrate fossils north of the Arctic Circle. And the first fossils that she found above the Arctic Circle were crocodiles and turtles. So we have a world that is Louisiana warm in the high polar regions. Here's a reconstruction we did for the American Museum of what the high Arctic looked like 55 million years ago. And of course, you know what it looks like today. It's a bit different. It applies not only to the land, but the sea as well. Here's an expedition in the early 2000s out to core the Lomonosov Ridge in the middle of the Arctic Ocean. And they cored that ridge, and they made a phenomenal discovery in the cores from the bottom of the Arctic Ocean in rocks that were 47 million years old. They found spores of, and they cored that long ridge, they found spores of azolla, a floating aquatic fern, which today grows in tropical, subtropical, and warm temperate waterways. And here's a picture of azolla covering a lake in Amazonia. That's the Arctic Ocean of 50 million years ago, a freshwater lake covered by floating ferns. In 1994 in Denver, we made an amazing discovery on the road south of Denver. This is 30 minutes from my office on Interstate 25 in the town of Castle Rock. And you can see along the shoreline, along the road edge, you can see those tarps covering our excavations. We found incredibly large fossil leaves. And it was an unusual site. There are a number of features about the site that caught us unaware and unexpected. And one thing I point out to you, if you go to tropical rainforests today and walk into tropical rainforests, they have a number of characteristics quite different from temperate rainforests. Extraordinarily high species diversity. In some places, as many as 300 or 400 species of trees per hectare of forest. One of the great fundamental differences between temperate and tropical rainforests. We did a survey in Yasuni National Park in Ecuador, and we looked at over 600 species of tropical rainforest tree leaves, and about 60% of them carry this weird feature, this elongated pointed tip, also known as a drip tip. It's a leaf drying adaptation. When it rains in tropical rainforests, the water beads up on the leaves, the water droplets go out these drip tips, drop off, the drip tip springs back, and within minutes after a rainfall in tropical rainforest, the leaves are bone dry because the drip tips have dripped them dry. And that prevents algae and fungus and lichens from growing on leaves and preventing the photosynthesis from happening. So it's a necessary adaptation where you have more than 80 inches of rain a year. And when you see a drip tip, you know you've got a tropical rainforest because of that temperature and leaf size. So we were delighted to see at Castle Rock in Colorado drip tips on 64-million-year-old leaves. Castle Rock, Colorado gets 14 inches of rain today. And here was evidence that it was a tropical rainforest at latitude 39, outside of the tropics. Biomes move. This is my friend Bob. I sent him on a task in Brazilian Amazon. I said, Bob, walk down the trail, pick one leaf from every tree you find, come back when you have 100 leaves. He came back with 100 species. That's tropical rainforest biodiversity. Here are the fossils from Castle Rock, Colorado, the same biodiversity. And we stumbled on it, but what we stumbled on was the oldest known tropical rainforest in the world, 64 million years old, not in the tropics. In a warm world, the tropics move to mid-latitudes. So we published this paper, A Tropical Rainforest in Colorado, 1.4 million years after the Cretaceous Tertiary boundary. That's the event that caused the extinction of the dinosaurs. I'll get back to that. Here's an artist's reconstruction of what Colorado looked like when it was a tropical rainforest 64 million years ago. And kind of amazingly, then, it kind of brings up the point that what did the world look like 64 million years ago? What was the distribution of biomes? Were there, in fact, any temperate rainforests at all? And one of the points I made in my abstract is, how ancient are temperate rainforests? And I would submit to you, and I will submit, oh, I'm so happy about that. I would submit that temperate coastal rainforests just aren't that old. But I'll get back to that. Now, that's my old, of course, not your old, so you'll be all right with that. But note this. Here's a prediction made by Morley in 2000 that, in fact, in a warm world, you would actually get 3 bands of tropical rainforests, one at the equator, and then one on each north and south mid-latitudes where you have ample rainfall, because you have ample temperature in a warmer world. It's just the rainfall that's the limiting factor. And in fact, Castle Rock appears to be evidence of that northern band. We've since been working in Patagonia searching for and finding the southern band of warmer rainforests. Now, if that's not enough, it turns out that in the greenhouse world you have spikes of intense heat. And we didn't even know anything about this at all until 1993. And the way we discovered these hyperthermals, which are these times of intense warmth in an already warm world, is through the deep sea drilling project and the offshore drilling project. And the most significant one of these events is called the PETM, or the Paleocene-Eocene Thermal Maximum. Happened around 55 million years ago. It was discovered by drilling into the sea bottom and taking up cores of sediments. And you can see a very pronounced spike in this graph. That's the PETM. In an already warm world, in a world that already had polar forests, there was an abrupt release of carbon into the atmosphere and a warming of 5 degrees centigrade in an already warm world, which brings subtropical climates to polar latitudes. Lasted about 100,000 years and washed out, but these hyperthermals are of intense interest right now because we are facing questions of what it's like to be in a warming world, and here is an amazing fossil example of a rapid warming in an already warm world. I mean, most of what we know about rapid warmings are from studying ancient glacial periods and the warming in the Greenland ice cap, where it warmed often and many times during the deglaciations of the ice age. It would warm 4 or 5 degrees in less than a decade. But that's in a glacial world, in an icehouse world. We're actually more interested now about what happens in a greenhouse world, because that's our future. These things burn themselves into the soils. These red bands in Wyoming are fossilized tropical rainforest soil horizons from the PETM, and you can collect the fossil animals out of these things. And amazingly, you have things like these little Hyracotherium or Eohippus, the Don horse. These animals are small. They're like a 12-kilogram or 12-pound horse, a very small horse. But when the hyperthermal struck and the world jumped its temperature 5 degrees, these 12-pound horses, these dog-sized horses, dwarfed to like 6-pound horses or Chihuahua horses. I mean, think about that. It's like amazing things. I mean, the fossil record holds these incredible tales of what happens as you rapidly change climate. Here's one. We discovered this gigantic fossil ant, a hummingbird-sized ant in Wyoming. And it turns out that giant ants today do exist in the tropics. And we see during the Eocene transpolar migration of giant ants. The most absurd title I've ever published, Intercontinental Dispersal of Giant Thermophilic Ants across the Arctic during the early Eocene hyperthermal. Truth is way stranger than fiction. All right, so I'm going to take you down to the southern hemisphere now. This is a polar view. On this map, you see the tip of South America, Antarctica, Australia. You see the distribution of that genus Nothofagus, the southern beech, very common tree. And explorers looking at the southern hemisphere for a long time were always amazed to see that the forests of New Zealand and the forests of Chile looked identical. And until I saw it myself, I didn't really believe it. But when you go down there, it is truly phenomenal. I mean, here's a forest in Chile, and here's a forest in New Zealand, and here's the Nothofagus of Chile, and here's the Nothofagus of New Zealand, and here's the Coriaria of New Zealand, and here's the Coriaria of Chile. I mean, how did this happen? It's a long way across that southern ocean with a great big ice-covered continent in between. And of course, the story is written in continental drift and changing climate both. It's not enough just to stick those continents together, because in a world where you have polar ice, you're not going to get forests to go from Australia to South America. And we've been working now in Patagonia trying to unravel this thing, searching for this southern band of rainforest. And we discovered in the late 90s this amazing place called Laguna de Lumco in Chubut province in Argentina. And today it's this sort of beautiful volcanic caldera, but it's a giant fossil lake bed, which can be ripped apart with jackhammers and the fossils extracted. And we pulled together this amazing record of the plants that were growing in Argentina during the global warming of 50 million years ago. And what we find are amazing things. We find genera that today are tropical genera of Australasia. Here's Papua cedrus, a conifer from New Guinea that was growing in South America 50 million years ago. Here's another rainforest conifer, Dacrycarpus, again, one from Australasia, found in Argentina. Here's Gymnostoma, one of the sheep pines. Today grows only in the tropical rainforest of northern Australia. Here it is as a fossil in Patagonia. And one of the great delights was to discover eucalyptus. Now, Australians are very proud of their eucalyptus. They have 700 species of eucalyptus, and it only occurs in Australia and New Guinea and associated islands. It turns out that the oldest eucalyptus in the world is actually in South America. So what you're seeing is this amazing connectivity across a polar region in a warmer world with the aid of plate tectonics. And you can see these continents closer together. It wouldn't matter a bit if you had ice in Antarctica, but if you forest Antarctica, as it was forested for most of its history. And the forests only left Antarctica about 30 million years ago. We have actual tree fossils from Antarctica as recent as 3 million years old. So you think about something as permanent and as icy as Antarctica and realize you could put a forest on it, it does kind of change your perspective about time and climate and vegetation. All right, so now I have to assemble the Pacific Northwest for you and build the rainforest that we're talking about for the rest of the symposium. I start 75 million years ago, which is really my favorite time. I prefer to be in 75 million-year-old rocks if given the option. And what's amazing about the world 75 million years ago is that North America was split into two halves by a north-south seaway that connected the Arctic Ocean with the Gulf of Mexico. So Western North America was actually a long peninsula of Asia, if you will. And the artist who did this image, Ron Blakey, has made these amazing maps. When you start making maps this detailed of ancient times, you realize you're making a lot of guesses, and you'll see in a second why this is maybe not the best thing. But note that he puts in a Bering Straits there, which there really is no evidence for. I would argue there's a continuous connection between Asia and this long peninsular Western North America. Here's another rendering of it. Look from the polar view, the Alaskan-Siberian Bridge, connecting Alberta with the Mongolian desert. Pretty straightforward. How do we know this? We recognize the same kinds of dinosaurs, Tyrannosaurid dinosaurs in South Dakota and Mongolia, Hadrosaurian dinosaurs in North Dakota and Mongolia, these amazing endemic aquatic plants in Heilongjiang in China and North Dakota. I mean, what you're seeing is continuity of an ecosystem across that bridge 75 million years ago. And so Beringia is not just the story of the peopling of North Americas, it's the story of the stocking of North America with its plants and wildlife for over 75 million years. Don't think that Beringia is a recent story. Beringia is a deep and rich story that's yet to be told. Here's taxodiaceous conifers from Kundur in Russia and North Dakota. You have this continuity of ecosystems across. And note, none of our modern temperate rainforest taxa. Then an interesting event happens at 66 million years ago. We were struck by a 10-kilometer asteroid, which caused a number of things. It caused the extinction of dinosaurs. It caused heavy extinction of plants in North America. And in many ways, North America is not just a post-glacial wasteland. It's a post-glacial, post-KT boundary wasteland. The southern hemisphere, this is probably the reason that the southern hemisphere maintains its araucarians and podocarps. We have them here in North America right up to the KT boundary, and they go extinct in North America. So probably what got rid of the araucarians and podocarps is an event, an extraterrestrial event. And imagine what your temperate rainforest would look like if you had Pinaceae and Cupressaceae and Araucariaceae and Podocarpaceae here in the Northern Hemisphere. It would be a different place altogether. But, you know, the asteroid struck and you don't have that, so sorry. Now I want to assemble North America, and the geology of the west coast of North America is stunningly complex. It has baffled geologists for the short few hundred years they've been studying it. It baffles them still. You'll rarely find two geologists in agreement on any topic about the geology of Western North America. So everything I'm showing you here is just what we know today, or what we think we know today. But I want you to just evolve the west coast of North America. And you can see that Alaska there, it doesn't look much like Alaska 65 million years ago. You can see the Arctic Ocean. You can see that North America grows by accretion. Island arcs slap onto the side of North America with sound effects and slide up the coast. So the coast is growing wider over time. Here it is at 50 million years, 40, 25, 15 million years, kind of starting to look familiar, 8 million years, 3 million years, looking pretty familiar. The ice comes, the ice goes, and here's today. Now, if you look very closely at southeast Alaska, this is supposed to be today. I don't think you'll agree with the map maker's rendition of southeast Alaska, but you get the general idea. This is a pretty amazing story, the story of accretion of land. So the land that we're on now started out somewhere in the Pacific Ocean and was slapped on. And how that happened and what it looked like and when that happened is still a matter of tremendous debate. Remember, moving continents at 5.9 centimeters a year, you can do a lot of stuff in 100 million years. You can slap on a lot of landmass onto North America. So in southeast Alaska, we're not only in a post-glacial landscape, but we're also in this post-accretionary landscape. And those two things together make this place extraordinarily difficult to study as a geologic and extraordinarily interesting to study as a geologist. All right, so there's a paper that was published called The Great Alaskan Terrain Wreck. And I'm just going to show you one extreme. I'm not even sure if I accept this or not, but here is one hypothesis of how Alaska came to be. And what you see are two bands. On the right-hand side, you see faintly recognizable the outline of Western North America with Vancouver Island on there. And off to the left, a long strip, an 8,000-kilometer long strip of land that was one of these accretionary wedges coming in over time. And what happens in this concept, in Stephen Johnston's view, the Great Alaskan Train Wreck, this giant train came and hit North America and then crumpled to the north like a train wreck, like the cars of a train coming off. And if you look at this diagram, and I apologize for this diagram, but you'll have to squint and see it, from left to right is the colliding and the crumpling, and if you squint over on the right, you can see your state of Alaska. The results of a train wreck. That's one interpretation of how Alaska came to be in its present formation. We do know that the west coast of North America is an accretionary story. We know it's a complicated story. The timing and details are very much to be worked out. But in that context, in order to have a rainforest here, you've got to have some land here to start with. So I've given you the land. Let's put the rainforest on it. Here's the Yakutat terrain, which is that area up in the Prince William Sound over to Yakutat area. That is a chunk of land that formed about 45 million years ago off the coast of California and drifted north over 45 million years before being emplaced on the southern edge of Alaska. An amazing thing, and you can see that in the right-hand diagram as it moves up the coast. Now, one of the problems for us paleobotanists is that imagine if this is exactly what happened. Imagine if plants were living on that landmass off the coast of California and becoming fossilized, and then they get carried up and smacked into the coast of Alaska. It makes for a kind of a difficult interpretation. Am I looking at the vegetation of California, or Oregon or British Columbia or Alaska. So it matters when these things hit. And you know, it makes my life quite complicated too, to kind of reconsider these ancient environments. And much of the interpretation of the paleobotany of Alaska has been complicated by this. Where was this fossil flora growing when it was growing? Was it growing in Alaska, or was it growing in California and then brought to Alaska as a fossil? That's not a trivial question. We need the geologists to help us figure that out. But it complicates the understanding of what the landscapes were here and when they were here. That having been said, we have amazing fossil floras in Alaska. Much work was done in the 1930s by a guy named Arthur Hollick. And then in about 1961, working with Don Hopkins of Beringian fame, a guy named Jack Wolf from the USGS dedicated about 50 years of his career to studying the fossil floras of Alaska. And I met Jack 30 years ago and worked with him. And his body of work really forms our understanding of the vegetation of Alaska for the last 50 million years, from this time of the warm world to the time of an icehouse world, and the evolution of the temperate coastal rainforest. So Chickaloon's up by Anchorage in the Matanuska Valley, and what you see are broadleaf trees and metasequoia. You see the same forest I showed you from Ellesmere Island. You see an Arctic warm world flora. You don't see a world dominated by Pinaceae. You see a world dominated by metasequoia and broadleaf trees. A deciduous world, likely, but a warm world. Why deciduous? The further north you go, the less light you have in the winter. So arguably, deciduousness is a clever adaptation to polar light levels, not cold winter temperatures. In Bellingham Bay, we have this amazing thing called the chuckanut flora, which has got cycads and palms, giant rainforest leaves. It's a bona fide tropical rainforest. In the Yakutat block, we find these same things. And one of the questions is, did we have subtropical rainforest in Yakutat, or was it growing off the coast of Washington and deposited in Yakutat? It's an unresolved question. So how subtropical were the floras of Alaska is an open question. All right, so the world goes from being a greenhouse world to an icehouse world about 34 million years ago. And what prompts that is the opening of Drake's Passage and the separation of Antarctica from South America and the refrigeration and eventual freezing of Antarctica. So we get ice in Antarctica starting about 34 million years ago, much earlier than ice in the northern hemisphere. And let's just do a quick review. In a greenhouse world, it's not your world. It's essentially ice-free. It's essentially grass-free. Grass is really an icehouse plant. The polar regions are forested. Polar sea surface temperature up to 20 degrees centigrade. Warm, swimmable water in the Arctic Ocean. Tropical forests at mid-latitudes. Equatorial sea surface temperatures approaching 35 degrees centigrade. Hot tub temperatures. And dinosaurs, but they got whacked at the KT boundary. This is not your world. This is not your world. You're icehouse people. All of your experience is icehouse experience. This is my world. I'm a greenhouse guy. What's the icehouse world? Bipolar ice caps, caps on both sides. We don't get them bipolar until about 5 million years as ice comes into the northern hemisphere. So for a while, we had a unipolar ice cap. From 34 million to about 5 million, we had ice caps only in the southern hemisphere. Sea ice, a nice innovation of icehouse world. Grasslands, savannas, Arctic tundra, and other icehouse biomes. These are biomes that evolved. Remember, biomes come and biomes go. Don't take your biomes for granted. Tropical forests at equatorial latitudes, where they ought to be. And large-bodied land and marine mammals. Mammals being the effective term, not reptiles. Okay, so now let's go now to up by Anchorage on the Kenai Peninsula. Down by Homer, there's a place called Seldovia. And in Seldovia, we have a pretty amazing fossil record from about 15 million years ago to about 10 or 9 million years ago. And this is what's called the Seldovia flora. And what is it? It's in the beginning of the ice house. Remember, the ice house has started in the southern hemisphere. What do we find? We find ginkgo and metasequoia and cercidophyllum and maple and alder and sycamore and liquid ambar and elangium and a number of other things that are growing at mid-latitudes in Japan. I mean, the flora of Kenai Peninsula 15 to 20 million years ago is the same as the flora of eastern Washington and central Japan. It's a broad-leafed, temperate forest. Broad-leafed, temperate forest. It's not a conifer rainforest. So even though the climate has started to change, it's not there. And if you look at that forest today, there are remnants of that forest left on our planet. They grow in the eastern United States, they grow in Europe, and they grow in eastern Asia. That's the mixed broadleaf deciduous forests. If you've ever spent time in New England or Manchuria or Europe, you know that forest. That forest was an Alaskan forest 15 million years ago. It's pretty amazing to think about it. And what's even more amazing is remember that Beringia is the doorway to North America. When we have three, we have the Isthmus of Panama to South America, we have the crossing of Greenland into Scandinavia, into Europe, and we have the Beringian access into Asia. And ultimately, those three portals are the portals by which plants and animals migrate into North America. And 15 million years ago, the kinds of animals we had here in Alaska were amazing things like this. This is Gomphotherium. It's a four-tusked elephant. Evolved in Asia, walked across the Bering Land Bridge about 15 million years ago, started showing up as fossils in North America about 14.8 million years ago. Here are your elk 15 million years ago in your broadleaf forest. Alaska didn't look like Alaska 15 million years ago. Now, what's pretty amazing, ultimately, is we start around 15 million years ago picking up the initial evidence of modern, what I would call the tree genera that compose the temperate coastal rainforest. You start finding nodules with Pinaceae cones in them. And you have this amazing record. And you can see on this, I don't know if you can read the scale, but in the Miocene warm period, and then it starts to cool. Somewhere around 10 million years, it starts to cool towards the ice ages. And that's when the fossil record of Alaska goes blank. We lose, the fossil record's not continuous. We don't know what's going on. We leave this world with four-tusked elephants and mixed mesophytic vegetation and anchorage without a temperate coastal rainforest as far as we know it. And the lights go out for 10 million years. We don't have any fossils. We have no story. The ice age comes. We have something like 20 advances and retreats of the ice age. The landscape gets dramatically brillowed. And when the lights come back on, we've got salmon. There's a fossil salmon, a million-year-old fossil salmon. And over at the University of Alaska here in Juneau, there's a mural by Ray Troll showing salmon in the forest. It's an artistic metaphor for the importance of salmon to the forest and how salmon come up, these anadromous fish come up these streams and leave their bodies and fertilize the forest and feed the people and the animals. This ecosystem, this incredible ecosystem, is really a byproduct of the Ice Age. When the lights come on, the Ice Age is over, here's your temperate coastal rainforests, about which I hope to hear a lot in the next 2 days. And I take you back to this diagram because when we figured this diagram out in this gathering of the National Research Council, we were a little bit stunned because what it means is that by the year 2100, under business as usual scenarios, we're going back to the Eocene. The Eocene is the world of forested poles, of bathwater Arctic Ocean. We're not talking glacial interglacial here. We're talking a world that's so utterly unfamiliar to us that only the paleontologists have seen it. What was remember that mixed broadleaf forest in Anchorage is only 15 million years ago at more or less our present CO2 levels. I mean, that's why you hear 350.org. Some people think that 350 ppm of CO2 is what destabilizes ice. And what's one of the big questions? We don't know the actual answer. Is what point do we destabilize ice? At what point in carbon dioxide in the atmosphere does ice become unstable on our planet? Very important question. Obviously, there's a lot of ice. It takes a while to melt. But I flew over Glacier Bay 2 days ago, and I was very impressed how much ice has melted between 1801 and today. I mean, you fly for a long time over vast open bays where there used to be ice when Captain Cook was here, and it's gone now. So ice is kind of a cool ephemeral product on our planet, and it's really a thing of the ice house. And I am very happy you're doing what you're doing because we are at a moment in Earth history like none other. Thank you very much.
Thank you, Kirk. We will entertain a few questions. Kirk will entertain a few questions. Brittany's here in the middle of the room. There is a mic station, and it might not be convenient for everybody to access it. And we're sorry about that, but we need that for the streaming video and the recordings that we're doing. So please, if you have a question, come to the mic station. We have 5-7 minutes.
Thank you for that great presentation. I've been wondering those things for a long time now. I got the big picture. I was just going to ask where the pine family came from that formed our present-day temperate rainforest. Did that come over from Asia? Do you know exactly from whence it came? Like all of our pine family that dominates the current temperate rainforest here, during that dark period when the lights are out, it came from somewhere. Do you have some ideas of where that, I think it's the interesting idea you've talked about, that our landscapes are very new, but our plants are very old. I'd like to know a little bit more about that.
There's sort of this interesting thing about the Pinaceae, because the Pinaceae is a family, has a deep geologic record. It goes back to the Cretaceous and Jurassic. But the genera, Pseudotsuga, these are very important Sitka spruce genera, those things, we see hints of them in a couple places. We see them at elevation, at sites that are fossil sites at high elevation. So the site called Republic in eastern Washington is a high elevation site. Remember, you can cool down by going north in latitude or going up in elevation. We see them, there's an amazing 45 million year old fossil site on Axel Heiberg in the Arctic of Canada. So as it starts to cool down in the Arctic, you start picking up Pinaceae, Larix starts showing up, Picea. And these things, I mean, that to me is the most stunning thing, is like, we don't really even know where the boreal forests and the temperate rainforests come from. They're very relatively recent, and they really are a statement of how important climate is for vegetation, ultimately. But they're ancient lineages that assemble themselves quite recently. So you have a fresh young biome here.
I have a question that deals with respect to the historians in the Tlingit culture. They would say in their stories, they would say, they would say, before this great flood happened, this particular event or historical type of thing took place. We have interpreted it to mean a great flood, but when we say on in our language, it means land. When we say qaslaqu, we're saying that the earth moved. And so I just wanted to ask, do you have any reference to either of those particular type of things in your studies?
Well, you know, it's an interesting thing. I mean, I come from a culture, too, that has its creation stories, and I've spent much of my life kind of wrestling how do you integrate the oral histories of cultures with the written rock record of the planet. And what's amazing is that the ice ages are quite recent. I mean, people were here during the ice ages. We know there are evidence of humans in North America during the ice ages, as you know as well. And the end of the ice ages are pretty interesting. When you sunder an ice sheet, you create tremendous floods. I mean, you take a huge amount of ice, 10,000 foot thick ice, and melt it on the landscape, it gets dammed, and those dams release, and you have tremendous floods. So in eastern Washington, the channeled scablands are evidence of vast glacial release floods. We see the same thing in northern Eurasia. We see the same thing in eastern North America. So the end of an ice age is associated very often with gigantic floods, much larger than anything we've seen in our modern times. So floods, ice, and of course, you know, as you heard me say, mountains come and mountains go. I have a dim view of mountains. They're very ephemeral. But on a human time scale, mountains don't come and go. So really, I think probably the reference that is probably appropriate is the one to ice and ice-based floods.
Okay, thank you.
You bet. Okay.
Our next talk is going to be by Dominick DellaSala. Dominick is an award-winning author of the book Temperate and Boreal Rainforests of the World, and he is shamelessly selling that book here in the back of the room or in Ballroom 2. He's published over 150 technical papers, testified in Congress on ESA and climate change issues numerous times, and appeared in nature documentaries and national press stories. He's the chief scientist and president of the Geos Institute, which is based in Ashland, Oregon, and the Geos is one of the 16 partner organizations in our partner network. And he's president of the Society for Conservation Biology's North America section. He's motivated by his daughter, Ariella, who's 7 years old, and leaving a living planet to her and all of her generations. And I just wanted to say on a personal and professional note that Dominick has spent an inordinate amount of time helping build the Symposium program, both this session and an adaptation session this afternoon. And he was on many a phone call, many a day, as we developed that program early on. So with that, please help me warmly welcome Dominick DellaSala.
Thanks a lot, Mike. It's great to be here back in Juneau again. And boy, Kirk's talk definitely changed my perspective on historic framing and backcasting. So I'm actually on the tail end of a book tour that I started during the International Year of the Forest last year. And I've been traveling around the globe from Alaska to New Zealand and areas in between, raising the visibility and profile of temperate rainforests, because when most people think about rainforest, the first thing that pops into their mind are the world's tropics, and rightfully so. Over 50% of the terrestrial species on Earth occur in that equatorial belt. But there are some really important places around the globe that aren't tropical, that are rainforest, and so the objective of the book was to raise that visibility level. And so I worked with over 30 scientists from around the world to put together the different chapters of the book that represent the regions of the world that qualify as temperate and boreal rainforest. And you're going to be getting a 30-minute glimpse at what that looks like, and hopefully you'll buy the book over on the side over there. And you know, this story really is about uniqueness of place. And that's what I've seen around the globe in my travels. The end of my book tour is going to culminate with a keynote at the European Congress of Conservation Biology, where I'll be speaking on the temperate rainforest of Europe. Yes, Europe has rainforests. And that's coming up in August. So let me see if I can get this thing to work here. Okay. So we live on an incredibly alive planet, which is forested. About a third of the Earth's surface is forested. I think that's working. And when you break down the different forest types around the globe, most of it is tropical, followed by boreal. And then you can see at the very bottom of the screen there, about 100 million hectares, or only 2.5% of the total forest cover, qualifies as temperate and boreal rainforest. And even though it's a low percentage, what I hope to point out in my talk today is how important these forests are on a global scale. Now, the flip side of this is that we're also on a trajectory of rapid deforestation and degradation around the globe. These are some statistics from the latest Global Forest Assessment released by the FAO in 2010. This will be in an article coming out in Conservation Biology that I led, that's coming out in the May edition of ConsBio. And it shows the deforestation forest degradation rates around the planet in different time intervals. And you can see behind me here that there are some areas that really jump out as deforestation hotspots. South America, Asia, Africa have deforestation problems. But curiously, it showed North America in a plus, an afforestation period. And I'll show you in the next slide that there's some problems with the metrics that were used by FAO in tracking deforestation. But I wanted to kind of put some numbers out there to see the extent of the global problem that we're dealing with. Let's see if I can get this. There we go. The current deforestation rate averages about 13 million hectares a year around the globe. Big number. So what does it really mean? I like to break down big numbers. It's about the size of the state of Louisiana every year being deforested around the globe. But for you Canadians in the room, about twice the size of New Brunswick each year. And so we keep breaking down that number to get a perspective on it. And it's about 88,000 football fields minus the end zones, or about 35,000 NHL-sized hockey rinks for you Canadians. That's on a daily basis. And for those of you visiting the campus of Southeast Alaska, an area the size of the campus is deforested around the globe every 3 minutes. It's a huge deforestation footprint, and clearly a global problem that we haven't solved yet in terms of our unsustainable relationships with the planet's forests. And so I mentioned that there were problems with the metrics in terms of North America because the way the FAO evaluates forests or deforestation is they have a very loose definition of what a forest is. Plantations are counted along with native forest around the globe, and that's a problem. In the US, we've had a major forest loss or degradation, and that has occurred through the loss of virgin forest. The intact forests mostly are gone around the lower 48 states, and Alaska is pretty unique in still having a big chunk of intact forest. If you add up the roads and the road building on the national forest alone, you could drive around the globe 17 times. And so those roads have a big impact. That doesn't show up on the FAO reports when the US reports to the FAO on its afforestation and forest degradation metrics, and it needs to. So what we set out to do with the book project was, again, shine a spotlight on the world's temperate and boreal rainforest. We wanted to come up with a working definition of what these forests are from a climatic standpoint. You'll see that in a little bit. We wanted to quantify them and come up with a seamless global map of where they occur and what their various percentages are around the world. And then we had a number of chapters that dealt with the question of how do we get to a sustainable relationship with our forests. And so here's kind of a very quick definition of temperate and boreal rainforest. There's a whole chapter on this in terms of the climatic conditions that are characteristic of temperate and boreal rainforest around the world. Paul Alabak had a lot to do with the development of these ideas, and I continue to thank him for his seminal work on temperate rainforests. But what we've done with this, with the book, was to use a computer model to take all the climate data for all the world's temperate rainforests and compile them. And so this is what you have behind me there. They've got very narrow annual temperature fluctuations. You can kind of see the temperature gradient behind me there. The mean temperature of the warmest quarter is still pretty cool. So even in the summertime, they're relatively cool. And there are differences depending on where you are. They are very wet places. Perhaps our definition is a little on the, for the low end of this is lower than any other temperate rainforest definition that's been published, but we have a whole explanation as to why that is important. There's compensatory mechanisms like fog and humidity levels that can allow temperate rainforests to persist in the lower end of the spectrum of precipitation. They have snowy winters in high latitudes, and up to 19% of the annual precipitation occurs in the driest quarter. That's really critical. because one of the key characteristics of these rainforests is their incredible richness of lichens. This is a characteristic that occurs around the globe. And while the tree diversity is low relative to tropical rainforests, there are some sites in BC, for instance, that have lichen richness that is off the charts and is probably higher than what we see in tropical rainforests. So that summertime precipitation is really important to the definition of what a temperate or boreal rainforest is. And so one of the things I had the opportunity to do when I was working on the book was to head up the, on top of the canopy crane facility in Washington. I got hoisted up in a little bucket. If any of you have ever been to that site, it's pretty extraordinary. And you're looking down on the rainforest canopy because that's where a lot of the life occurs. It's in the soils, it's in the canopy. It's very different than the tropical rainforest. When I was talking to NPR, they said, well, give us some sound. And I really struggled with that because I'd been to tropical rainforest and the sound is deafening. It's just an incredibly alive forest with birds and all kinds of insect sounds. But when you get into a temperate rainforest, it's very quiet. And it's because a lot of the biodiversity is below us and above us. And so to get up into the canopy was a real blessing for me to witness. You can kind of see the bucket that you get hoisted in on this canopy crane. And the lichen richness is really extraordinary in these rainforests, as I mentioned. Whether you're here in the Northwest or you're in England's rainforest, the lichen diversity is one of the key biological characteristics. Another important aspect that we talk about in the book is the carbon sink value of these rainforests. Acre for acre or hectare for hectare, many of these temperate rainforests are among the most carbon-dense, carbon-rich forests on Earth. And this is important from a carbon sequestration standpoint. What we did was some back-of-the-napkin calculations. We haven't gone through peer review on this yet. But when you add up the amount of carbon sequestered and stored in these rainforests, and you compare that to the equivalent emissions, global emissions, from all the world's energy use and all the world's emissions, you could see the difference there. The amount of carbon stored in these forests is about 6 times the annual CO2 emissions around the planet. So they play a pivotal role in helping to stabilize the global climate. And of course, the flip side of this is deforestation contributes to global warming pollution. You can see the bar graph behind me from the IPCC assessment that shows forestry as number 3. And surprisingly, forestry contributing more to the world's CO2 emissions than the entire world's transportation sector. So we are definitely having an impact in terms of how we manage forests and how we are treating the climate commons. And so let's get down to the nitty-gritty. This is kind of the virtual tour of temperate and boreal rainforest, kind of on speed. I've got to go through a lot of areas. I'm not going to hit all of them, but you can kind of see the map behind me. We identified 10 definitive regions of the world. The way we did this is we had a handful of regions, plugged in the climatic variables that are associated with those handful of regions, and then asked the computer to generate a predictive map of where the world's temperate and boreal rainforests are. And once we had that predictive map, I went out and found scientists to work with, who wrote the chapters to make sure that the model, the computer model, made sense. And so that's what you have behind me. The areas that I have circled on the map are places that qualify as boreal rainforests. Now, most of the world's boreal forests are not rainforests. They're circumpolar in their distribution, they're much drier. But the 3 that you see circled behind me are boreal, but also have enough precipitation to qualify as rainforest. And so here's where they occur. And in the Pacific coastal region of North America, we have over 1/3 of the world's temperate and boreal rainforest. Europe, surprisingly, comes in number 2, and then so on down the scale. Now, the difference with Europe is that most of their rainforests have been transformed. There's very little intact areas except for portions of Russia. And so this aerial extent map that you see behind me, or figure you see behind me, has nothing to do with forest quality or forest intactness. It's just a relative measure of percent. And so here's the quick virtual reality tour. And I'm going to skip over these areas pretty quickly because they're going to be covered by other folks on the panel. Gordon Oriens is going to be talking about Pacific coastal rainforest. But I'm just going to hit a couple of the high points that are made in the book. On this chapter in particular, we were really fascinated with the Tongass rainforest. And I spent some of my early days back in the 1990s as a research biologist up here on the Tongass, and I was always fascinated with the incredible rainforest here. And what pops out on a global scale with the Tongass is its world-class salmon fishery. There is no other place on Earth that has as many wild salmon runs as Southeast Alaska does. This region also is only one of 4 relatively intact temperate rainforests in the world. BC with the Great Bear, Tasmania, which I just got back from in November, Chile, which I was in a few years ago, and Paul Alabak is going to be talking about, have portions of their forest that are intact. That is it. The rest of the regions are highly fragmented systems. And so what we have here is truly global in significance. Highly productive rainforest system, as others have mentioned, it's not just the terrestrial, it's the combination and the overlap, the ecotones of marine, freshwater, and rainforest that make this place so special. And again, back of the napkin calculations, it's a carbon warehouse. If you take some numbers in terms of what the average tons per acre of carbon stored in the old-growth forest, you come up with a figure that can then be converted to carbon dioxide equivalents, and you compare that to Alaska, the state of Alaska's annual emissions, and these rainforests are doing work. They are performing the service of absorbing a lot of the emissions that we're putting up into the atmosphere and hanging on to them and storing them over long periods of time. And of course, the intact areas are absolutely significant for a number of reasons, including their carbon values, their salmon values. You can see the map behind me that shows the remaining intact blocks, the really large ones in dark green. This was produced by Conservation Biology Institute a number of years ago. We're going to zoom in now on Prince of Wales Island, where I did my earlier research. Okay, so this is a time series that's going to show you decadal changes in logging and roads that show up from the 1960s forward. Let's see if we could get that to work. Nope, it didn't. Try it again. I don't have a third eye behind me, so you have to tell me if it's showing up for you. Okay, good. So we're going from the 1960s forward. Every flash you see on the screen is a decadal change in Prince of Wales Island in terms of road building and logging that has occurred there through 2000. And so this is the story that you see around the globe, whether you're here on the Tongass rainforest or you're in Chile or other places. And why the statistic I showed earlier is a bit misleading because it doesn't look at issues of intactness and forest fragmentation. Now, I threw this one up here. This is the interior wet belt rainforest of the inland region of BC. And I threw it up here because we seem to be stuck on temperate rainforests, calling them coastal. And they're not all coastal. There are at least 2 examples of inland temperate rainforest. The one here in inland BC and also in inland southern Siberia that qualifies as rainforest and is not directly associated with a maritime environment. And in the inland rainforest, it's pretty extraordinary. The tree that's being measured here is a western red cedar that is estimated at over 1,800 years. Very old, ancient trees. Maybe not as ancient as Kirk's analysis of paleobotanical history, but certainly ancient in terms of a human lifespan. I guess it's all relative. And this particular system has its large carnivore assemblage all intact, which is also relatively rare. And it's driven by this association with the lichen food web. And a lot of those lichens are supporting the base of the food chain for caribou and other species that feed off of them. So it's a lichen-driven rainforest food web. And it's in trouble. So you can see a satellite image here, the Swiss cheese landscape behind me, and also the GIS analysis that has been done of clear cuts in red and its impact on the caribou herd. So just like we have issues on the Tongass, there are also issues in the inland rainforest of BC in terms of fragmentation. Now I'm going to zip quickly to the southern hemisphere and only spend a few minutes there because Paul Alabak is really going to hit this one pretty hard in his comparison. But I had the opportunity when I was with World Wildlife Fund to visit this region. We were considering this a sister ecoregion. There was an exchange program. At the time I was working in the Klamath-Siskiyou region, and I got a chance to visit the Chileans and take a look at their rainforest. And it felt to me like I was in Alaska, but someone had flipped the globe on me. It looked a lot similar to Alaska. The glaciers were there, the rainforest looked similar to a certain degree, big trees were there, and so it really is an extraordinary place, as Paul will mention in his talk. But the thing that really fascinated me about that system is the level of endemism across the taxa, and this is extraordinary for a temperate system. When we think of endemism, we tend to orient our minds towards tropical systems, but in the case of Valdivia, most of the taxa are endemic, and they have ancient lineages that go back to Gondwana affinities, and there's this mixing of neotropical and Gondwana affinities, and it makes it a really rich temperate system that is off the charts in terms of its uniqueness. They also have their share of old-growth dependent species, like Magellanic woodpeckers and the rufous-legged owl. They're a kind of analog to our northern spotted owl, I guess, and some of the same logging problems that we see elsewhere with multinational corporations having this kind of impact on the Chilean landscape, with a good chunk of that being deforested or heavily fragmented now. I just got back from Australasia, and I got a new definition of size matters. Everything there is big. The trees are tremendously big, the tallest hardwoods in the world. The eucalyptus trees that you see at the top screen there, the largest living eagle in the world, the wedge-tailed eagle, and the largest crustacean, the Haida. And I know that probably would look good with some butter on somebody's plate, but it's a freshwater crustacean, and it tends to occur in the older forest types. And when you start to add up the carbon in those forests, and this is based on, whoops, how'd that go forward? It's based on a paper that was in Nature a few years ago. Again, I did that. They also are doing their share of absorbing a good chunk of Australia's annual CO2 emissions. And Australia just passed the resolution for a cap on their emissions, but it hasn't extended yet over into their land use. And so hopefully they'll get the picture that these big trees, these rainforests, are part of their attempt to curtail their emissions, and they could have an impact on how Australia addresses implementation of their new emissions policy. It's a very rich place. And when I was walking in these forests, I was in a mixture of subtropical and temperate elements, lots of different colorful wildlife species, koalas, gray goshawks, all kinds of parrots, wedge-tailed eagles. Pretty unique place. And the big fight in Australia right now is in Tasmania over the mixed eucalypt forests. And in the book chapter, we argue that these should be treated as rainforests, because in the absence of fire, they are a fire-dependent system, but in the absence of fire and when there's enough moisture present, they will succeed the rainforest. And so this is where a lot of logging is occurring, and the native temperate rainforests are off limits to logging, but Australian government doesn't consider the eucalypt forest rainforest. So you've got trees that are over 100 meters tall that are being chipped into wood chips and sent to Asia because of a difference in definition. And so we make a strong point in the book that these should be captured in a reserve design in Tasmania, and there's some progress moving in that direction. The government just agreed to a moratorium on logging their temperate rainforest in Tasmania, but it's unclear whether or not the moratorium extends to the eucalypts. When I went over to New Zealand, I had the opportunity to visit this kind of rainforest. It's a mixture of the podocarps that Kirk was talking about. A podocarp is different than our seeds and our conifers, which are all seed-based on the cone. The podocarps have, the cone is largely fused, and one or two of the seeds come off of that cone instead of the whole cone being seed viable. And the podocarps are really interesting species, and this rainforest has a mixture of broadleaf and podocarp species that distinguish it. And here's some of the tree sizes in that rainforest. This is a totara, which is a type of podocarp. And you can see the girth on that tree. That's my daughter standing alongside of it for scale. And so I also visited the giant kauri trees in the North Island of New Zealand. And I put the bus up there because it's really hard to get a scale of the size of this tree. This is wider than any redwood I've ever seen. And the girth on this tree is 16.4 meters. And so that would be equivalent to 2 buses that size parked bumper to bumper. If you parked it behind the tree, horizontal to the tree, you wouldn't be able to see the buses. So that's how big that, or wide that tree is. But they don't grow very tall. They only reach about 30 meters before they start branching off into the canopy. They certainly don't grow as tall as our redwoods, but man, those are magnificent trees. And so unfortunately what's happened in New Zealand is that at one point it was estimated that there were approximately 1.2 million hectares of those giant kauri trees. There's only 140 or so hectares left. And so they've done this, like the rest of the examples I've given, to most of their big trees. And this is going back to Maori influences and European contact, so it's been going on a long time. And so they don't log their native forest anymore in New Zealand, but there aren't many native forests left. And so the message there is not to let our forests get to the point where we don't have much left before we stop logging our native forest. And that's the situation that's happened in New Zealand and in Australia as well. So here's where I'm headed next. I'm headed to Scotland to give a keynote on Europeans' rainforest. We have a chapter in the book, and you can see that behind me, places where Europe has rainforest. And these aren't the giant trees that I've shown you before. A lot of them are sessile oaks and birches and rowan, and some conifers. It's a bit different. It's a lot different. But there's a lot of similarities in the lichen species and the climate, so it qualifies. And up in Norway, you've got a mixing of the deciduous that integrates to boreal as you get north, and some of the highest latitude boreal rainforest in the world, or the highest, at 70 degrees north latitude, they have boreal rainforest. And so that's where I'm heading next. I don't have time to get into other areas that also showed up that were some surprises in our project. Iran, Turkey, Georgia, South Africa, and the Caucasus in Central Europe have rainforest. And although Kirk might not consider 1.8 million years old, at least the tertiary affinities in the Caucasus are relatively old compared to the rainforest assemblages that we have in our temperate system. So it's all, I guess, dependent on perspective, but there are some older temperate rainforests that occur in Europe. And so I'm not a big fan of the Homeland Security Advisory System, but since I give this talk a lot in the public and people don't generally know what threat levels are, I kind of related it to the Homeland Security Advisory System, and this is based on levels of intactness and conversely fragmentation and other threats to these rainforest systems. And I think they're fairly obvious, but when I put this up and gave the talk in New Zealand, I got a lot of flack from rightfully so, from the folks in New Zealand that I had ranked their forest as too safe. And the big problem in New Zealand is exotics. they are overrun with exotics, not only in their plantation, but their native forests are being overrun by all kinds of exotics, so the threat levels needed to be elevated. And I did. I had it down low, so I bumped it up to guarded. Okay, so a couple of closing points. This is a paper coming out in Conservation Biology that I co-authored with Reed Noss. What you see on this side of the screen are science-based targets. They generally are based on representation, viability goals, etc. And for all the examples that we have on this side based on science-based targets, they come in at about 50% of an area needs to be in some level of protection in order to sustain it. What you see on this side are politically driven outcomes. So this is what the scientists are saying. This is what happens in reality. So in this article, we're calling on conservationists to think boldly, to actually ask for what nature needs. And thinking boldly, there are some examples with the Great Bear Agreements. I know that it hasn't been totally solidified yet, but they're approaching those levels. There's an example with the Tongass and the work that Trout Unlimited and Audubon Alaska and the commercial fishing groups are doing to get protection for their salmon areas. These are examples of thinking bold. And I'm going to close on this slide. I know Mike's trying to give me the hook here. The International Year of the Forest, the bottom line message that I've been given is that, you know, it depends on whether you think the glass is half empty or half full, but the reality is the forests are in crisis, and we shouldn't deny it, and we need to find new ways of messaging about that. Why I've given them the forgotten label for temperate rainforests is because they're not part of any of the global accords to reduce emissions from deforestation and degradation, and they ought to be. And what needs to happen is we're on a collision course right now with these forests because of unsustainable economic growth and economic pressures and climate change. We need a new ecology of economics. And while Peter stood in front of you yesterday and said he was pro-growth, I'm pro-steady state economy because that's what I think we need to get toward in order to have a sustainable relationship with these forests. And by that I mean at least half for nature, based on science-driven goals, a steady state economy that focuses on restoration objectives and operates within the carrying capacity of these systems, payment for ecosystem services, regulations, laws, etc. There's a lot in the grab bag, but we need to get to a sustainability goal here pretty soon. Otherwise, these forests are going to be history in our lifetime, or many of them will. So thanks.
Thank you, Dominick. Folks, we have a break until 10:30, and I encourage you to get with Dominick or Kirk and ask more of your questions then. We'll see you at 10:30 back in here.